Hello, and welcome to today's lesson. We're entering our new unit, Circles and Polygons, Unit 1. Okay, so you're going to see more circles and polygons as we work through the course. But this is our first introduction into these topics. Okay, Lesson 1, we're looking at our essential learning goals. By the end of the lesson, we will be able to define and draw a diagonal. Okay, recognize the difference between an equilateral, equiangular, and regular polygons, and classify polygons up to 12 sides. So when we look at polygons, the first thing that we want to do is define what a polygon is. Okay, it is a closed figure. Okay, so it has to enclose a space formed by connecting line segments, endpoint to endpoint, with each segment intersecting exactly two others. Okay, so when we're building polygons, we have to have line segments that are connected endpoint to endpoint, and each line segment connects with two other line segments at their endpoints. Okay, so we can see here the difference between a polygon and a non-polygon. Okay, let's say why these polygons are, or why these shapes over here are not polygons. Okay, here there's only one line segment. It does not enclose a space. This one starts to look like a polygon over here, but we don't have enclosed space on the left-hand side. And then our last shape that we have here at the bottom, okay, it is not made up of line segments for that shape. Okay, when we're naming them, we name them based on the number of sides. Okay, we need at least 3 sides to make a polygon, so we can't have a polygon with less than 3 sides. Okay, we're pretty used to our 3-sided polygon is a triangle. A 4-sided polygon is a quadrilateral, and then we start working down the list all the way through when we get to our larger sets of sides. Okay, once we get past 12 with our dodecagon, all we do is we just call it an n-gon. So you could have a 13-gon, 14-gon, 15-gon, okay, and it would continue on for as many sides as you have. Now, how do we name pentagons? Okay, or name a polygon? This one here is a pentagon. But when we're naming a polygon, we want to list the vertices in consecutive order. Okay, now, when we're listing them in consecutive order, what we can do is we can start with the first letter alphabetically and work our way around. Okay, so we could name this pentagon A, B, C, D, E. Okay, that is a possibility as well. But as long as you start with a point and you go in consecutive order around the shape, you can actually name any pentagon in any order you really wish. We could start at A and work this way around the shape. So we could name this one A, E, D, C, B. Okay, definitely a little bit harder to think about and grasp when it comes to naming. Okay, but know that as long as you start at a point and you work your way around one direction or the other, naming all the vertices, you have named the polygon. When we name triangles, okay, a very special type of polygon, one that we use most in geometry, we want to use the triangle symbol. Okay, so we have a triangle TSU. Okay, we could also name this triangle STU. We could name the triangle UST. Okay, we have a lot of ways that we can name this as long as that we're going in a consecutive order, starting with one point and working our way around the shape. We can't be wrong. Now, why do we need to use the triangle symbol? This shows us that we're dealing with the polygon shape. Because if I said TSU, what else could I mean? I could just be talking about an individual angle. So that's why we need the triangle symbol in that situation. Now, a few more vocabulary pieces that we have here. When we're looking at consecutive angles, okay, consecutive angles, okay, we could have ABC, or in this case, we could name it just angle B, because there is no other angle that we could make with B. And angle C share a side. Okay, so they are consecutive. And remember, when we're talking about consecutive, we're starting at one point and we're working around in either direction. So consecutive angles are angles that are next to each other as you work your way around the shape. Same thing with the consecutive vertices. Okay, we've got a vertice here at A, a vertice here at F. So we're not talking about the inside angles anymore. We're actually just talking about the points, and that's what a vertice is. It's a corner point or a point where two segments come together. Consecutive vertices are just, once again, working around in one direction or the other, okay, to find that next vertice, that next angle, or the next side length. So when we talk about consecutive sides, AB would be a consecutive side with BC, or, because we're going in this direction, or we could go in this direction. The fact that BA is consecutive with AF. Okay, so understand, it shares an endpoint. When we're talking about consecutive, we're working our way one direction or the other. Now, when we're talking about the diagonals of a polygon, the diagonals connect two non-consecutive vertices. So when I'm talking about diagonals of this hexagon, I can't connect A and M or A and T because those would be the consecutive vertices, but I can connect A to H, I can connect A to S, and I can connect A to E. Okay, so if you think back in one of our logical reasoning units, we actually had you do this connection as we went through. Okay, line segment, no arrows on the top. If you wanted to put the dots on both sides, you can. Okay, we usually list them alphabetically, but we wouldn't have to. So for this last diagonal, I could name it EA, and that would be okay. Once again, using the segment symbol on the top, because they're segments, they are not lines. Okay, two more pieces of terminology, and we're almost done here for this lesson. We have a convex polygon, a polygon in which all diagonals are inside the polygon. Okay, when we look at a triangle, remember we don't have any diagonals. It has 0 diagonals. But if I look at this quadrilateral, or in this case it's a trapezoid, okay, we have one diagonal because I can't connect to the consecutive sides. Okay, same thing here with this shape. It looks like a square. All we know, though, initially is that it's a quadrilateral. Okay, when we look at the concave polygons, okay, we have a polygon at which at least one of the diagonals is outside. Okay, so if I look at this vertice here, here are my two consecutive ones, so I can't connect there. But if I connect to another vertice, you can see how that segment or that diagonal that I created is outside of the shape versus the diagonals on the left here being inside of the shape. Same thing here. We could see from here to here, it would be an outside diagonal connecting non-consecutive vertices. We would have another one here, okay, and that's the difference between concave and convex. Okay, last piece for our lesson today. Equilateral, equiangular, and regular. Okay, now, if we have equilateral, The tick marks tell us that all of the side lengths are the same. Okay, so if we have any length measurement, we could put the length measurement in all of these pieces. Now we have to be careful because sometimes pictures can be deceiving. Can we say that all of the angles in this picture are congruent? And the answer to that is no. So even though it looks like they're all 90-degree angles, what we don't know is this could be tilted ever so slightly, and we just can't see it well. And it could be turned into what we call a rhombus. A rhombus is a quadrilateral, 4 sides, equal length, but the angles are not all equal to each other. Okay, equal angular. Now that we know all 4 angles inside of this shape are equal. Now, can we say that all the sides of this picture are congruent? And you can probably guess the answer to that is also no. Think about what could you do to this shape since the side lengths are not locked in. What we could do is we could shorten this shape up. And now we can see that we've turned something that looks like a square into a rectangle. So we just don't know the length of the sides, so we can't assume that the picture is accurate. Okay, and now finally, if we put it together, a regular polygon. As soon as you're given that word regular, it's the best thing that we know. All the angles are equal to each other and the same measure, and all of the side lengths are equal to each other and the same measure. So now, do I know that this shape is a square? Yes. All 90-degree angles, all of the side lengths are the same. Okay, finishing up here. What does it mean for 2 triangles to be congruent? What parts of the triangles are congruent? So this is just a look at, another scenario here. What we have to understand, all angles equal. So we've got our 1, our 2, and our 3 tick mark side. Over here, we've got our 1, 2, and 3 tick mark side. And we've got our 1, 2, and 3 tick mark angles. So if I'm running to write what we call a congruent statement, and we'll see this as we continue on through Geometry Part 1 into Geometry Part 2, we want to make sure that we're matching the pieces. So if I want to call this triangle A, B, and C, if I'm matching a congruent triangle, I'm matching angles and I'm matching sides. So A is the 1 tick mark angle. I have to start with X, which is the 1 tick mark angle. B is the 3 tick mark angle, so I need to find the 3 tick mark angle for my next piece. So I'm making sure that each one of these pieces is matching either based on their tick marks in the angle, or if I'm looking at BC, BC is the 3 tick mark side length. So I have to make sure that I'm using the 3 tick mark side length and going from the right point to finish up the naming of this triangle. That concludes our lesson. Have a great day.